Take a look at this rendering of a Menger sponge, a fractal geometry that continuously folds inward infinitely. Material scientists want to build these perfect, non-repeating structures physically at the microscopic level to engineer highly advanced materials. The first barrier they faced is traditional manufacturing. Nanofabrication usually relies on photolithography, a messy process requiring chemical resins, temporary polymer scaffolds, and physical molds. But the second, harder barrier is physics. As we see in this diagram, standard light has a strict resolution limit. A laser beam cannot physically focus into a point smaller than roughly half its own wavelength. That hard limit means you cannot simply take standard optics and 3D print or carve out a highly intricate sub-100 nanometer fractal shape. Because of these optical limitations, the fractal geometry remains trapped as an unbuildable mathematical ghost, perfect on paper, but impossible in physical reality. To bypass the need for physical molds entirely, researchers shifted their strategy. They decided to create the exact geometry out of intersecting beams of pure light. This diagram shows holographic interference lithography. Overlapping coherent laser beams generate a precise, stationary landscape of distinct peaks and valleys. By continuously adjusting the angles and number of these intersecting beams, they transform that simple grid into a highly complex, three-dimensional standing wave. That standing wave matches the exact spatial blueprint of our desired fractal. The researchers have successfully projected the mathematical ghost into the real world. The catch is that, right now, it is constructed entirely out of immaterial light. We still have a major scale problem. Even with our light blueprint, a standard 355 nanometer UV laser projection is physically too large to create true nanoscale features. To break past the diffraction limit of standard optics, scientists utilize a phenomenon called surface plasmon toleritons, or SPPs. This animation illustrates the SPP mechanism. By coupling the optical UV light wave with a metal dielectric surface, the light induces collective electron oscillations along the boundary. This physical coupling process directly compresses the geometry of the light wave. By translating the optical wave into concentrated electron oscillations, they shatter the diffraction limit, successfully shrinking the blueprint down to a sub-100 nanometer scale. The final challenge is figuring out how to fill this microscopic light blueprint with actual solid matter. They achieve this using a technique called plasmonic optical tweezers. This visualization shows plasmonic optical tweezers using localized electromagnetic hotspots to pull floating silver ions directly into the wave's peaks. Traditional optical tweezers require intense energy, but this plasmonic method operates on lower laser power, which prevents the delicate ions from being destroyed by the heat. Once the ions are trapped, we reach the climax of the process, direct ion photoreduction inside the optical trap. This diagram breaks down the reaction. The intense electromagnetic field peaks instantly trigger a chemical conversion, reducing the floating liquid silver ions into solid metal atoms. Because the light itself drives the chemical reduction, the metal crystallizes instantly into the exact shape of the standing wave, requiring zero polymer scaffolds to hold the structure together. What you are looking at here is the final result, a perfectly formed sub-100 nanometer solid silver structure that exactly matches the infinite complexity of the Penrose-Menger geometry. We are no longer carving away bulk material to get a shape, and we are bypassing wasteful, toxic polymer molds entirely. This scaffold-free process establishes a direct pathway to manufacture complex metamaterials for building advanced optics and highly precise quantum components. It works because diffractive optics, plasmonic forces, and chemical reduction are all perfectly synchronized to operate at exactly the same time. By mastering the fundamental forces of localized light, we can command individual atoms, literally crystallizing pure mathematical ghosts into physical reality.